I want to welcome you all here to ISTC. We have another one of our speakers in our sustainability seminar series for the spring. This spring, as many of you know, we've kind of shifted our emphasis a little bit and are looking at some social science aspects of sustainability to go along with the different scientific and more technical issues we've looked at in the past couple years. All of our seminars are archived on our website if you're interested in some of those past topics. Today, we're very pleased to have Scott Butner here with us, all the way from Washington. Scott's a senior research scientist in Knowledge Sciences Group at the U.S. Department of Energy's Pacific Northwest National Lab. Scott joined PNNL in 1984 after receiving his BS degree in chemical engineering from the University of Washington. For the past 27 years, he's been involved there in a wide array of renewable energy, pollution prevention, and sustainable technology research projects for the lab and its clients. Many of his research projects examine ways of better utilizing information technologies to improve environmental decision-making by business. For the past 3 years, Scott's also helped to lead the laboratory's techno-social predictive analytics initiative, an internally funded laboratory-directed R&D effort intended to bring together scientific and engineering models with social science and behavioral models in an effort to better understand the interplay between technological and social systems. So Scott's been active as a member of the American Institute of Chemical Engineers and has participated in over 20 of their national institute meetings, and he's also the past chairman of the Institute's Environmental Division. Scott is also served as the Information Technology Workgroup co-chair for the National Pollution Prevention Roundtable and has been a regular presenter at the workshops that they have for more than 15 years. Scott lives in Richland, Washington, and as an added aside, when he's not tinkering with computers, he's an avid, and some would say fanatical, fly fisherman and semi-professional photographer. So please welcome Scott Butner.
Thank you, Nancy. Just for calibration's sake, everyone in the back of the room can hear me just fine? Okay, great. I'm always a little leery speaking in front of a group this large. If I were to give this seminar at the laboratory, even though we've got 4,800 employees, I might have a third of this many. So I'm flattered. Thanks for showing up, and only a tiny bit intimidated. Let me do a quick survey just to see who I'm talking to, what kinds of backgrounds. How many of you are actually social scientists or work in the social science area? Okay. How many in engineering or physical sciences? Good. I like to see that. Because as you may have heard in my intro, in my bio, I am also not a social scientist. And we'll talk about that in a little bit when I get to the disclaimers, but I always like to make sure that I'm calibrated reasonably well to my audience, and I think there might be a chance that we can do that. The second calibration point, Gary? The second calibration point I always like to check on, especially when I'm far from home, is to find out how many people have heard of Pacific Northwest National Laboratory. I'm impressed. That's a lot. Okay. So that means maybe a third of you have not. For that third, just so you aren't left totally in the dark, Pacific Northwest National Lab is, I guess your closest equivalent to that would be Argonne National Lab, is one of about 10 U.S. Department of Energy national laboratories scattered around the country. Our emphasis historically has mostly been in engineering as opposed to basic sciences, although over the last 10 years we've made a pretty good stab at producing a physical sciences, or a fundamental sciences footprint as well. We currently have about 4,800 employees working primarily in energy, environment, and homeland security. And the homeland security work has recently, some of it has been in the news because we have a lead role for the Department of Energy in nuclear nonproliferation, and that includes a lot of devices for monitoring radiation from testing of nuclear devices. And so consequently, we were the first laboratory in the United States to detect radiation from the Fukushima nuclear power plant as it reached the shores here in the U.S. Of course, being on Washington's coast, or being 200 miles from Washington's coast helps a little bit too. But having ultra-sensitive detectors that can pick up that kind of trace amounts makes a bit of a difference. But I'm not here to talk about that kind of work. I'm actually part of a group that looks at multidisciplinary, interdisciplinary work related to a variety of knowledge representation and computer modeling techniques. And through that involvement, I've had a chance to work in a lot of areas related to the environment over the last 27 years. That's what I went to the lab to work on. I actually spent my first 10 years at the lab physically building laboratory systems, mostly biomass reactors, and testing out the reactors. But the longer I worked in biofuels, the longer I worked in energy efficiency and pollution prevention, the more I realized that you really can't discuss these issues without talking about behavior. You can't make good inroads into getting people to adopt new technologies without understanding what motivates people to change from one technology to another, change behavior from one set of behavior patterns to another. And that's what we'll talk about mostly today. The slides that I'm going to present, most of the discussions I'm going to present revolve around my role on an initiative called the Technosocial Predictive Analytics Initiative. I'll talk about that initiative a little bit further into the presentation. In fact, why don't I just go ahead and give you the outline. The first is what to social scientists seems like a question with an obvious answer. To many of the physical scientists we deal with at the laboratory, at our own laboratory, isn't quite so obvious. Many of them seem to view sustainability as largely a mass and energy balance problem, right? It's just about making the resources we've got stretch far enough, and if we have the right technology, the rest takes care of itself. Well, that's a pretty simplistic view of the world. I don't know a lot of physical scientists that hold on to it much longer than the first couple of years they work in the field, but it's the point of view that many engineers come to the field with before they've actually started working at trying to get technologies into the marketplace. So after a brief introduction, we'll talk about 3 problem vignettes, problems that we've actually been tackling at the lab. One is predicting future program impact. This is sort of on a micro scale. This is looking at how do I decide how to make scientifically defensible predictions about what impact I'm going to have in out years if I deliver technical assistance. I think that's relevant here because you guys are one of the states and one of the programs still delivering technical assistance. And there are many states where that's not happening anymore. But here in Illinois, there's still a viable technical assistance program, and trying to figure out how we look at what's the impact of the technical assistance visit I pay today on the adoption of new technologies 3 years from now is a question that's right on the top of minds of funders and researchers for that matter. Understanding conservation behavior. Why is it that we have such a hard time actually seeing reductions in real energy, in actual energy use when we develop more and more efficient technologies? If you look at the literature, if you look at people's behavior, you find that we tend to use more of the good, more of the resource, or use it more widely for uses we hadn't before as technology becomes more efficient. So if I deliver a more efficient air conditioning system, people put air conditioning in more homes. Or they turn on the air conditioning earlier in the summer and leave it on until later in the fall than they would have previously, as opposed to actually gaining that improvement in energy efficiency. And then we'll talk about food, climate, and regional security. So we've gone from the micro scale of looking at how do I measure and predict the behavior of one particular program that might be funded at the state or regional or even city level, to questions of what happens with the interplay between food, climate change, and biofuels in a region like South Central Asia, Bangladesh, Pakistan, and India. And this is a set of problems that we were asked to look at by some of our intelligence community clients, to look at what happens to regional stability, to political stability, as we make different kinds of choices about priorities between food versus fuel, and for that matter, as the climate changes the availability of cropland. So those are the vignettes we'll talk about. I'll give a brief overview of the TPAI initiative, touch a bit on the modeling approaches and how we've applied them to these 3 sets of problems, and then just a real brief overview of some future directions that I'm personally motivated to look at for my own research. And I'd like to leave some time at the end for discussion and certainly questions and answers, but you're welcome to introduce or to interrupt me during the talk as well. But first, I have to have my 3 disclaimers. What is it? Wait, don't tell me on NPR that has the audience read the 3 disclaimers. Mine are a little different, not nearly as much fun. I am not a social scientist. I have spent most of the last 15 years in close proximity to everyone from linguists to sociologists to economists and working on a daily basis with them. And I've spent most of the last 3 years managing research projects or overseeing the budgets on research projects that were managed by PIs who came out of those disciplines. And so I've had a long-standing interest in the role that social sciences can play in better allowing us to take advantage of technology advances. I'm still a technologist at heart, and I don't apologize for that, but I do think it's important to let my biases be known. Secondly, I'm going to assume a pretty broad interpretation of sustainability. I have been around long enough to have been through definition wars, and Dave knows what we're talking about here. Definition wars for pollution prevention back in the 80s and early 90s when we fought over whether recycling was part of pollution prevention. I was a abstainer from those wars and a conscientious objector from those definitional wars. Likewise, I'm a conscientious objector from the definitional wars over sustainability. There are all sorts of definitions floating around. I tend to revert back to the Brundtland Commission definition of, creating a future that does not impede the ability of future generations to meet their needs in an equitable manner. That's a great definition from a standpoint of guiding philosophy. It doesn't give us much to go by in terms of metrics or outcomes that we're striving for. I try to gloss over that, frankly. I believe that pollution prevention I believe that sustainability encompasses climate change, which I'll talk about. One of our problem sets looks at climate change issues. You can't have a sustainable society without addressing the climate change issue. Likewise, you really can't address climate change without addressing pollution prevention. And you can't address pollution prevention without addressing energy efficiency. And so while it may seem sometimes that some of the problems that I'm going to be talking about and that we're dealing with are really small subsets of the broader sustainability envelope, they're all components of it. And I'm satisfied with that if I'm not spending adequate time addressing the big picture, the capital S sustainability. My apologies in advance. Finally, I'm going to focus primarily what we're doing or have done recently at Pacific Northwest National Laboratory because that's what I'm responsible for. That's what I can bring uniquely. There are people in the audience who are probably more familiar with the broad body of literature in the social sciences as it relates to sustainability than I am. But I can tell you quite a bit about what's going on at PNNL. Pardon me. So, to start out, why the social sciences? Like I said earlier, when I talk to engineers who are working on new solid oxide fuel cells, they're working on new biofuel approaches. Many of them, if they are heads-down researchers working at their lab benches, trying to develop new technologies and haven't had a lot of exposure to the marketplace or to the policy issues, when you start to talk to them about sustainability and talk about living within a constrained set of resources, it's pretty hard for them not to go to the notion that this is a material and energy balance question. And in fact, at its core, I believe sustainability really is a material and energy balance question, right? I mean, we're trying to preserve more than simply the sustainable use of resources, but that's a big part of it. And it's an inescapable, necessary but not sufficient condition that we have to achieve in order to have any kind of sustainable societies. We have to live within the material and energy constraints we've got. But it's certainly not a sufficient condition. And any time you've spent, or if you've spent any time at all in the field trying to get people to adopt new technologies, if you've spent time looking at the policy issues of how do you decide which technologies are going to have impact on, for example, redistribution of jobs, redistribution of wealth between communities that are currently empowered and communities that aren't, redistribution of technological power from one region of the country to another. So, for example, the Pacific Northwest currently has some of the greenest power in the entire country. As we look at locating and siting green building or green infrastructure and green jobs, the Northwest would seem to have a disproportionate advantage, largely because of our unique geography. We've got lots of wind, we've got lots of hydro, and we've got lots of biomass for that matter. So we've got lots of resources that can work towards a sustainable future. So trying to decide how all these things are done fairly is certainly not a technical problem alone. And experience actually suggests that improvements in technology aren't enough even to achieve just our pollution prevention goals. Simply providing people with improved technology, with greener technology, is not a sufficient motivation to get them to change. Spend a day in the field talking to a small business person about making changes to their core business processes or to their manufacturing process, and you discover that pretty quickly. It's certainly not enough to achieve climate goals, and I'll show you some slides to that effect in just a moment, nor to achieve any degree of sustainable society. So sooner or later, and usually sooner, it comes down to the behavior of individuals is an absolutely essential issue to think about, to talk about when we talk about sustainable development. One is getting them to move beyond efficiency. Providing more efficient technologies is only part of the equation. We also have to move to pretty significant changes in behavior and lifestyle, and I'll show you some slides that show how that fits in, for example, the level 1 scenarios for climate change predictions, the ones that look at trying to stabilize CO2 at current levels by the year 2100. To anticipate unintended consequences. This is actually an area near and dear to my heart because I come out of a background of environmental life cycle analysis. And while life cycle analysis currently focuses largely on attributional LCA, on the attribution of environmental impacts to a technology and allowing you to make marginal comparisons between what's a million BTUs of energy from wind costs me in terms of environmental impact versus a million BTUs of energy from coal. That kind of comparison of the marginal impact of two different resources is often called attributional LCA. There's a different kind of life cycle analysis that looks at what happens when wind technology takes over and becomes a dominant technology. How does that change the rest of the system, and what are the environmental impacts of that change? There's something that's pretty close to home for us, and that's called consequential LCA, life cycle analysis, I should mention. And it's emerging slowly but surely as an important part of life cycle analysis, but it's not where most of the emphasis currently gets placed. A good example that I like to use to talk about that difference between attributional and consequential LCA is when I talk to students at Washington State University, where I teach a life cycle course. And the example is to look at the difference between one windmill, and I've seen a few windmills on the drive down here from Chicago, so I know that there are a few of them around here. And what is the impact of that one windmill versus the impact of, say, building 7,000 megawatts of wind power in a small corridor? Currently in Washington State, Washington and Oregon along the Columbia River corridor, about a 50-mile stretch contains roughly 7,000 megawatts. That's 350, is that? No, 3,500, I'm sorry, 3,500 current size wind turbines that are either sited and built already and spinning, or are in the process of being sited and built. And there's a big difference in the impact between a single windmill and multiplying that out times 3,500, because suddenly I've developed an enormous amount of infrastructure that I was probably not accounting for in the initial life cycle analysis. If I try to do the attributional LCA for that single wind turbine, I'm going to look at the road that went in, I'm going to look at the energy that it took to produce the windmill, to construct the windmill, and to maintain it. I'm going to look at all the chemical costs that went into that and the environmental impact I get out of it. What I will miss are things like, how does that change the nature of the communities where suddenly I now have 100 windmills within a 5-mile radius, and I have to have workers that are sited there nearby. I have to develop a community around those windmills because I've developed an industry that essentially needs its support infrastructure. I've changed the way people think about rural areas. A lot of the windmills in Washington and Oregon are in wheat fields that may have population densities below 5 people per square mile. And when I suddenly put in the road infrastructure to get the repairmen out to the wind turbines, to work on the turbines on a weekly basis or daily basis, I start to change people's norms and expectations about how far away is this little community of Dayton or Touchy. How likely is it that I might decide to move out there instead of living in the local urban hub? And so I change lots of systematic issues that have to do with, that create their own environmental impacts. Another one unique to the Northwest, or actually not unique to the Northwest, but we have a unique way of having to deal with it, is the fact that that wind is concentrated in a very small geographic area. And so I can have 7,000 megawatts that goes from spinning at full capacity to being shut down completely in the space of just an hour or two as a wind system moves through the region. And because that power is so close together, I now have to have a lot of capacity for matching the load on the grid when the power goes down or when the power comes up. And since we do a lot of our power matching, a lot of our grid management on the basis of hydroelectric, and hydroelectric has a lot of implications for how the water behind dams is stored and used. It has huge implications for our fishing industry because it affects salmon migration, has implications for our barging traffic and how we move grain up and down from the wheatlands of eastern Washington and Oregon down to the port cities in Portland and Vancouver. And so I've suddenly got a whole set of environmental impacts that have to do with unintended consequences of having lots of wind as opposed to 1 or 2 scattered windmills. Finally, because any modern definition of sustainability looks beyond purely the environmental and energy and economic impacts and considerations and tries to address social considerations of sustainability, we have to look at some sense of equity. How does this technology affect different populations, different demographics of people, and does it do so in a way that leads towards a more sustainable society from a sociological standpoint? Are resources, our jobs, our opportunities distributed more fairly? Does it concentrate power? Does it concentrate wealth into smaller communities or into fewer hands? And so those are also questions that are legitimate to ask. And we've actually been doing some studies on the implications of biorefineries and widespread use of biofuels on rural communities and how that might actually change the economics of rural communities that are actually typically pretty depressed right now because they've historically relied on a couple of resource extraction industries and haven't been doing too well, lumber and fishing in particular. A few more bullets for why behavior might be important. We'll actually talk about most of these further in the talk, so I'm just going to kind of skim over these. But from the research literature, my colleague Ben Shui, for example, did a very extensive study on consumer behavior and life cycle analysis and found that in her work at the household level, that consumer behavior is responsible for the majority of direct and indirect energy consumed. So behavior has a huge impact on how we use energy and how much energy we use at the household level. We're doing quite a bit of work right now with Bonneville Power Administration and other utilities on smart grid issues, especially looking at smart grid stability. As we get a grid system that is more and more distributed in terms of decision making, where appliances can actually be shut down at the individual household level or browned out at the individual appliance level, how does that affect the stability of the grid? And people's behavior affects this because people have to go along as willing partners in most of the smart grid models that are out there and actually agree to allow the utility to take over some control of those devices. Economists will tell you, well, it's all a matter of pricing. Price it properly and you'll get the response you're looking for. That doesn't seem to really bear out in the literature or in common practice. It certainly hasn't happened in fuel prices, for instance, because it turns out that energy consumption is pretty inelastic. It responds significantly only to really punitive levels of price increase, so consumers are constrained. If the price of gasoline suddenly increases, it doesn't mean that I live any closer to work. And so my commute distance doesn't change. And maybe if the price of gasoline remains punitively high for months and months and months, I might start thinking about either changing my mode of transportation or changing my commuting patterns. But typically over short periods of time, people simply grin it and bear it. And we have all been there because we've seen the price of fuel fluctuate so much over the last few years. Okay. So transforming, reducing, shifting consumption patterns requires a detailed understanding of how these patterns of energy use work, not just at the qualitative level. And this is, qualitatively is interesting as a engineer, and many of my engineer friends say, well, isn't all this just pretty obvious? I mean, intuitively, we know how people respond to changes in price. We know how people respond to different signals. And on a qualitative scale, that may be pretty true. When we're trying to model this and make predictions about the future and actually make investments, make technology decisions, make policy decisions, we need a little more quantitative certainty. And we need uncertainty bands around how much the fluctuations might be. So we look to modeling to do that. And I think with that, I'm going to move on to the next slide. So I'm going to talk about 3 problem vignettes because these provide 3, I think, pretty good examples of how we've been applying social science modeling at P&L. And I should caution you that if you came looking for research results, you'll get a few, but not that many. Mostly what we have got is work in progress, so you'll see some framing of problems and how we're addressing the problems using social science as opposed to published results. Although in a few cases there are some literature references I can point you at by my colleagues. And so the first is, how do I predict the future benefits of technical assistance? We've already talked about this a little bit. And hopefully I didn't scare away the AV guy, right? So this is one that I know is relevant here because Tim Lindsay, before he left, was working on this issue. A number of the rest of you have worked on this issue, I'm sure, which is understanding what makes a technical assistance program efficient, what makes it effective, how do you really change behavior, and how do you measure that behavior. In this case, we're actually doing work for EPA, and I'll describe that in just a moment, that looks at how do you predict behavior once you've actually gone out and delivered the technical assistance. The next one is looking at the role of behavior in achieving climate goals. And here we're going to look specifically at household energy use and some work that we've done with the Residential Energy Consumption Survey, which is I think, biannual census or survey of energy use patterns in homes, and looking at how you can use principal component analysis to tease out what the key components of household energy use are, if you want to try to model that. Finally, we'll take a look at a much bigger picture story, which is the use of modeling, in this case systems dynamic modeling, to look at climate change and food availability in a large region of the world where climate change is likely to displace something close to 500 million people over the next 100 years, depending on which climate scenario we end up with. For that, we do that, though, let me just give you a little background on our initiative, on the Technosocial Predictive Analytics Initiative. This is an internally funded initiative that we began in 2007 at the laboratory. Now, if you're not familiar with how national labs work, most of our funding comes just like it does at a university, from writing competitive grants and research proposals to various federal agencies. In some cases, we actually compete or partner with universities. In some cases, we're working on programs that are more targeted to things that national labs do uniquely well, and so we compete amongst the other labs for that funding. But a portion of our funding is discretionary and comes out of overhead funds that we charge on every research project. And so we have what's called LDRD, Laboratory Directed Research and Development Budget, that essentially allows us to make internally guided investments that are aimed at figuring out where our future ought to be. These are projects that are usually trying to be 5 to 10 years ahead of where the federal agencies are with their own investments, so that we can create capabilities within the laboratory that might serve our clients better down the road. I know that universities have similar kinds of internal investment programs. This is how we do ours. Typically, we do about 10 of these programs per year. This one was funded at about 4 to 5 FTEs. The usual funding curve, and I'm sorry, this probably won't show up on the video. The usual funding curve looks something like that. If this is year 0, year 1, 2, 3, 4, and 5. So typically there's a little ramp up while we figure out and further define the initiative, where 1 or 2 people might be funded to help define the initiative. 2 to 3 years worth of funding at full level so that we can actually put principal investigators on projects and let them set their research teams loose. And then a phase-out year, which is where we're at right now. We're currently wrapping up this initiative and essentially just trying to publish as much work out of it as we can and talk to clients about the results of the work. The goal of the initiative was to combine, or is to combine, modeling of technical systems such as power grid modeling, climate modeling. We have some of the best regional scale climate modelers in the country in the form of Ruby Long and a few of her coworkers who have been able to take climate models, take them from large grids and break them down to very small grid size so they can look at the impact of climate change scenarios on regions of the country, such as the Pacific Northwest, and make predictions about how does the climate, an overall climate scenario of a 3-degree temperature rise, for example, impact the progression of the wet season and the progression of the growing seasons in the Northwest. And agricultural production models with modeling of social and individual behavior. Because we're a multifunction laboratory, meaning we serve lots of different federal agencies as clients and we do research in a lot of different areas, we tried to have applications to intelligence analysis, particularly things like regional stability analysis, so looking at how different technologies were likely to impact strategic strength or vulnerability of different countries, of our own country for that matter. Applications to energy conservation. We do a lot of work with the Department of Energy's Federal Energy Management Program and their building energy programs. So a lot of work on looking at how do you get people to change behavior at the building level, and then broader sustainability issues. Oops, I keep wanting to go to the keyboard to switch that. The initiative had 3 research areas. One is the one I'm going to talk about today, the technosocial modeling. That was really to develop new modeling approaches, or at least new to us modeling approaches. Second is knowledge inputs, looking at how you acquire data and manage data to support these models. This is largely work that I've been involved with as a principal investigator, focusing on the use of semantic wikis and other tools to try to manage large amounts of data and tie it directly to the models so that we can aggregate and manage data that eventually drives our models. And then cognitive enhancement. In later years, we actually started just calling that what it is, which is applied gaming. Use of video game technology to help explore the models and understand how different scenarios might play out. And we found these were very good tools for analysts to use to explore potential scenarios, not necessarily very good for providing defensible scientific predictions about the way the world might work. And so I won't talk much about 2 and 3. In the technosocial modeling area, we've had a number of different thrusts, but the ones probably most relevant are looking at dynamic scenarios, which is really the use of systems dynamic models, mostly within an existing commercial framework called Stella. the vulnerability of food and food security and energy infrastructure to climate change, and then the impact of climate change and energy use on the power grid. Looking at how consumer behavior and distribution of consumer demographics might impact different kinds of grid models under climate change scenarios. We've used a variety. Oh, go ahead. Sure.
Can you expand more on the first one?
The first one.
Yeah, dynamic scenarios.
Yeah, so a lot of this, I've got it included in there for completeness sake, but is not terribly relevant to a sustainability agenda. But this is work looking at issues related to nuclear nonproliferation, so nuclear trafficking. Let's see, I guess the illicit trafficking demo that we just completed is the best example, where we're looking at how do you model the movement of nuclear capability, weapon capability primarily, between countries. How do you actually identify early markers of a country that's trying to develop a nuclear weapons capability, from everything from patterns of publications to patterns of student visas, political interactions between the countries. The propensity to proliferate is actually an area where we built a fairly extensive Bayesian net model that looks at what are the factors in terms of deciding whether a country is likely to try to go the nuclear weapons route or take some other means to assert regional or global power. And so that set of modeling tools really revolved around that issue, although there was some related work also simply on an opportunistic basis that came up, and we were asked to focus some of our energy on it, looking at modeling the proliferation of IEDs in Iraq. And that was actually just an extension of some of our propensity to proliferate models. They seem to lend themselves to being extended in that direction. And we happened to have a staff member come back from an extended period of service over there where that had been his responsibility. And so he came back in, and we built some models based around his expertise acquired in the field. And so that first area has relatively little connection to sort of classic environmental sustainability, but I included it for completeness in the initiative. Sure. In terms of modeling tools and approaches, we focused largely on the use of Bayesian nets. How many of you are familiar with Bayes nets as a... Okay, I've got one computer scientist back there, or electrical engineer. So I'll talk more about Bayes nets in just a moment, because that's how is behind the solution set to our first problem that we talked about. Statistical regression modeling. As a chemical engineer who's used to doing process modeling, I always have a hard time using the term modeling associated with statistical regression techniques, but nonetheless it does allow us to create models that predict behavior, future behavior based on past behavior. And this uses a technique known as principal component analysis to take a large multidimensional data set and reduce it down to some pseudo variables that usually bundle up several variables all together and can be used to determine what are the most important correlations within the data set or within the set of variables. Systems dynamic modeling, which is basically modeling the flow of materials, energy, information. And here we're using a commercial tool called Stella. And then I won't talk about it any further today, but we have started doing some work in agent-based modeling to look at behavior at the individual level. Most of our work looks at behavior of groups. But agent-based modeling, we believe, allows us to take a reasonably realistic look at the behavior of individuals within groups and sort of statistical likelihood of certain kinds of behavior emerging. It also allows us to look at emergent behavior in ways that we can't do with these more straightforward modeling techniques. There we're using a modeling framework, JADE, which is a open source Java agent-based tool, which allows you to create distributed models that can reside on multiple computers, essentially allowing the agents to operate on many different machines and have all the results come together. There's probably more than needs to be said about that for this presentation. back to the problem vignettes. I talked about predicting future behavior or future benefits of technical assistance. This is an actual TPAI technology, some of our work in Bayesian nets, that turned into a funded EPA research project to support a very specific program. How many of you have heard of EPA's E3 program? I know a few of the pollution prevention people have. So Chris Pierre and Tom Murray back at EPA had heard me talk about some of the BayesNet modeling and asked if we might be able to apply it to problem set that they have, which is trying to make predictions and most importantly, defensible predictions to Congress about what the future benefits are of delivering technical assistance through the E3 program. For those of you who haven't heard about it, E3 is fundamentally, the three E's are energy, environment, and economy. And it's basically a technical assistance program facilitated through the NIST manufacturing extension partnerships. And in partnership with EPA, it focuses on using supply chain connections or relationships between businesses to deliver technical assistance out to a large collection of companies within a set geographic area. It's simply a different delivery model for doing technical assistance. It happens to rely pretty heavily on lean manufacturing techniques, but I don't think that's central to the success of the program. The problem is that, like most technical assistance programs, the results that they get are often delayed by 1 to 2 or 3 years. And Congress was, of course, looking for justification on why should we invest in this program and how can you tell us what the program will actually do to benefit. So we needed a way to estimate program benefits in out years. We wanted it to, instead of simply being a good story to tell, which is what we often end up doing, that it could actually be validated with real data that is being collected from the field. And I think importantly, we wanted the model to have sufficient descriptive power to allow what-if scenarios to be explored, to be able to say, if I shift my emphasis in my program deployment from financial incentives to repeat engagements with the company, how does that affect the effectiveness of my program? Does it change the way in which I get benefits, that I get companies to actually implement technologies and to reduce waste? Our basic approach was to develop a BayesNet model of technical assistance. Now, for those of you who aren't familiar, and that was almost all of you, BayesNet is simply a way of representing a set of beliefs about the way the world works. If you're familiar with EPA's efforts and I think NUMOA's efforts on logic diagrams, and I think a bunch of you, by your show of hands, few of you have heard of logic diagrams. It's simply a way of taking my conditional belief that if I do an activity, if I deliver a technical assistance talk at a facility, that I can estimate the probability of some outcome, some second state occurring. So a very simple two-node Bayesian net would say that I have an input state, which is whether or not I've delivered technical assistance at a company site, and an output state that says what's my belief that that company will then reduce their amount of waste by some percentage. And you can chain together these beliefs or these statements about how the world works into long, elaborate chains, and I'll show you the ones that we're working on, and multiply out the conditional probabilities and end up with a quantitative model that estimates how the system is likely to change in response to different activities, and in this case, or to different parameters. And I think this will be pretty obvious when we get to the model itself. So our basic approach, though, because what we have as input from the field is really not a bunch of Bayesian nets, but we have instead a collection of recommendations from the NIST manufacturing extension partnerships that say, here are the projects we've recommended to the company. And they typically have associated with them some set of project and company attributes that we'll discuss in a second, some set of project metrics, so an estimate of how many tons of waste are going to be saved, how many BTUs of energy, how many jobs will be created. And we have that for each of these projects. And for a given site visit, I might have anywhere from 1 to 100 projects that have been recommended, although typically it's in the 10 or so range. What we are doing then is creating a model that says, given these attributes, what's the probability of success in year 1, 2, 3, and 4 for each of the projects? We then re-aggregate all that information and provide an overall estimate for the effectiveness of the site visit and of the overall pilot program in each of the states where they're operating. And I apologize, I normally don't like to do eye test charts. I didn't realize it was going to be this large of an audience. But I'll read you a few of the project technical attributes. So each of these are what we see as likely inputs, and we're currently going through validation of this model. But good examples are, is this a core technology? In other words, is this a technology that, does the change that's been recommended affect a fundamental technology for how the company does business? Is it part of their intellectual property? Is it part of their core manufacturing, or is it ancillary? So is it a key fabrication process step, or is it parts cleaning? If it's parts cleaning, maybe the company's less inclined to, or more inclined to make the change because I can bring in an outside vendor to do that, or because it's not central to the way I make my company or make my product. Let's see, this one is related to that. Is it proprietary technology? Is there a pilot opportunity? Some types of manufacturing facilities work with parallel manufacturing lines, and so I have the opportunity to set aside one of the lines as a pilot line, and I can test out a new technology without risking my overall ability to produce the product. If I don't have that situation, then my likelihood of implementing the technology is reduced because I've got a lot more technical risk involved. Is shutdown of the facility required to implement the change? Is the change at the product level? In other words, do I have to reformulate the product? In which case I might have a lot of concern, not only expressed by my internal technical stakeholders, my engineering department, but by my marketing people, by my customers, by all sorts of folks. Is it a change at the process level, or is it a change at the procedural level? We then go on to look at project business attributes. For example, is there an internal champion for this particular project? Is it something that was previously identified by the plant management or employees as an issue that they wanted to address? Does the company have in-house or only external capacity for adopting the technology? In other words, will they have to bring in outside engineers or consultants to adopt it? Is external funding required? Is it relevant to the strategic plans of the company? As you can see, these are largely non-technical aspects of the project, relating more to the business itself and how they behave at the business level. Then I have company attributes. Do I have good access to capital? Do I have management buy-in to the overall technical assistance activity? In other words, is this a grassroots effort with no management buy-in and support, or is this something that was bought into by the upper management? Looking back at the Everett Rogers sort of view of the world, are these leaders, followers, or laggards in terms of their technology adoption? And often these are things, and you notice these are all either binary or simple, yes, high, medium, low kinds of assessments. These are assessments that can be made in the field, oftentimes by the field person on relatively short notice and relatively simple basis. They don't require a great deal of numerical data to generate. What's the churn rate? And this varies from industry to industry. So is this a type of industry, a type of technology, or a type of company where the technology tends to change over frequently? Or is it something with a large sunk capital investment, a pulp or paper mill, iron foundry, where maybe that change doesn't occur so often? And then in the interest of time, I didn't realize how fast I was going here. There are also some program attributes. Currently, E3 is being piloted in several states around the country, and each of the pilots is implementing it with slightly different configuration of how they deliver the service, what other services they're delivering. So this looks at, for example, does the client have to contribute a copay? Many of the programs, because they're running through NIST, the clients actually pay something up front to have NIST come in and do the assessment. But in some cases, the program copay can be rebated or refunded back to the company if they successfully implement any of the suggestions. Is there a pre-existing relationship between the technical assistance provider and the company. If there's not, that often is less likely that the initial set of recommendations are going to be implemented. How often is the technical assistance team out at the facility? Are they out there just once or twice, or are they out there repeatedly? Each of these become factors that then feed into the likelihood of success in year 1, year 2, year 3, and year 4. And we're in the process of, so I have, for visual simplicity, left off the lines, but you can imagine the line coming from each of these nodes connecting to each of these years. Essentially a big wiring diagram that propagates the conditional probabilities forward to each of the outcome states. Whoops. And from here, what we're doing is we're working with a technical assistance program in just one moment, and I'll get your question. Down in San Antonio, Texas, and collecting data from 17 site visits that they've done and all the implementation details that they've tracked over the last year and a half. That's one way of calibrating the model, is to actually build the conditional probabilities based on a training set of data from the field. Where data are sparse, and we expect that they will be in this case, the other approach is to use expert solicitation. And here we've been working with a technique known as conjoint analysis, and what we do in the case of conjoint analysis is we make a large number of pairwise comparisons. We've developed some web-based tools for doing this. But we'll say, we'll post the question to a number of experts, and we'll say, for example, everything else being held equal, which is more important? That the company has a pilot opportunity to use a pilot plant approach or set aside a pilot line, or that they have a high strategic relevance of the project. And we'll use a 5-point Likert scale to assess where on that scale of most important to least important, a group of experts feels that particular node happens to be in the likelihood of success. And then we reduce all the data from a large number of those runs, and we found that that's a pretty effective way of not necessarily calibrating to the way the world works, but to the way the experts think the world works, which is, in the absence of real data, sometimes all you can really hope for. Okay, now I'll take the question.
Year 1, year 2.
Right.
There's 29%, and I was wondering why it's not.
Oh, I'm sorry. These are kind of blurred together. So one of the results of a Bayes-Net approach is that I can predict the likelihood of any state, but the states have to be discretized. So instead of having a continuous number come out of here, what I can do is I can say there's a 10% probability of less than 10% chance of success. And there's a 90% chance that it's going to be up here in this upper category, that it's likely to be adopted.
What jumped at me was
And-
it's not 30%, it's 29%. All of the numbers are...
Yeah, and that could be just a residual goof on the principal investigator's part, in which case I'll plead guilty. So, but that's a good catch. So this project is actually currently underway. We've constructed the initial model. We're currently working with the San Antonio E3 program to collect pilot data from their delivery of services and do an initial calibration of the model. But we'll also be talking with other programs around the country to try to get additional data and run additional training sets. Okay, Nancy, I should stop for just a moment. Time-wise, I was shooting for an hour. I've clearly gone past that.
Well, we can keep going. If individuals need to leave to class or other meetings, they feel free to leave, but I think
Okay. All right. So the second set of problems is the role of behavior in achieving climate goals. Why is that important? Here's a level 1 scenario from MIT's climate modeling scenarios from their integrated assessment model. What this looks at is, so the level 1 scenario basically projects out to the year 2100. It's, I believe, the scenario that predicts global stabilization of CO2 at current levels by 2100. And I always confuse these model scenarios because there's so many of them. But you can see distribution of energy by source. If I remember my color code correctly, we have gas, oil, gas, coal, and nuclear. And then in out years, we show the increasing use of renewables. What you'll notice is that if you look at current straight-line energy projections in terms of where we think we can get with current technology or expected improvements in existing technology, and where we need to be. So we need to be down here at this baseline, right here. Then we have a large area bounded in these gray boxes that essentially amounts to behavior change. That in order to get down to the climate scenario where we actually stabilize CO2 levels, almost half of our energy savings have to come, or half of our projected energy use from a straight line projection has to come from changes in behavior, changes in the way we commute, changes in the way we use electricity in the home, changes in the way we do pretty much everything in our lives, the way we consume products. So behavior change becomes pretty important. Just some more data to sort of back this up. This is all collected from by my colleague Tom Sandquist out of our P&L Seattle office, who is an expert in residential and commercial energy usage. This just looks at the fact that even when we have gains in efficiency, and let's see here. So if we look at site energy intensity, which is a reflection of the efficiency of, or the amount of energy used per unit of activity in a residential site, or per capita, even though that's going down all the time, if you look at actual energy, primary energy use, we see a continuing rise. And the reason for that is the sort of normalization of people's expectations about what they should expect in their household. For example, I didn't include it in this set of slides, but Tom has a great slide showing the increased use of air conditioning on the West Coast. I'm 52 years old. I grew up in the West Coast at a time when air conditioning was never found in a house west of the Cascade Mountains. And it would really be unthinkable because we might only have 10 or 15 days a year where a normal person would expect to use air conditioning. We have a pretty temperate climate and low humidity, generally low humidity, except for during the cool season. And yet these days almost every house is built with air conditioning on the West Coast. And so as our energy efficiency goes up, we tend to use that savings as an excuse to implement the technology more widely. As our television energy efficiency goes up, we have, not necessarily because of any causal relationship, but just coincidentally, started using more televisions. And so now we have more televisions, bigger televisions, and the actual energy use per household continues to go up overall, despite big improvements in efficiency. So Tom set about to look at a project to understand the factors which contribute to residential energy use patterns, develop a statistical model that could be plugged into our technical model. Remember I said that the TPAI was focused not on social modeling per se, but on the integration of social modeling into technological modelings, and in this case grid models, to look at how energy use along the grid is being distributed and gain insights into how behavior might change smart grid behavior. The smart grid, you're all familiar with the basic concept? Okay, I'm seeing lots of heads nodding yes. So from our literature reviews of the subject matter, Tom found a few things, worth noting. That simply providing information like bill stuffers or promoting attitude change doesn't really reduce consumption very much. I don't know how many of you get the bill stuffers in your home energy statement. I do. I don't pay too much attention to the general request to save energy, although one of the things that I will look at is, wrong button, is mentioned down here, these normative comparisons. Providing examples of specific behaviors can reduce energy consumption substantially, but again, adoption is limited. Energy consumption feedback reduces usage by about 2 to 15% depending on method. In other words, if I have some of the smart grid pilots have run with energy meters in your home. You can actually see how much energy you're using in real time. Much like owners of Priuses are familiar with the gauge on the panel that shows them their current miles per gallon. And I know more than one Prius owner that drives very much according to that gauge, has that up there almost as much as the speedometer, because it becomes a game to them to try to, and a matter of pride, to see how high they can push their fuel efficiency. Yes? Pardon? This isn't available online, but I'm happy to send you an email, and I can also get you back to the original reference, which is probably more important than simply me mentioning these numbers, because I've got some original literature sites on this. So just make sure that you grab my card before you leave, and be happy to get you. Tom's got a couple of publications to, what is it, ACEE, I think it is. And so if you look up Tom Sandquist and energy conservation, you'll find his papers. But I'm happy to send them to you as well. Normative comparisons are useful. How many of you have seen the stuffers that come with some energy or utility bills that show how you're doing relative to the rest of your community? It turns out that those are actually more effective in changing behavior than simply asking people to reduce their energy usage. So showing people how they're doing relative to community of their peers, this normative calibration, it turns out to be an effective technique, and it helps to drive a lot of these higher end energy reduction techniques. Higher frequency feedback is better, so real-time feedback ideally might be the best. One of the things we've been playing around with is looking at how to use the social media, and particularly Facebook and Twitter, to try to encourage very short duration energy conservation during things like the time leading up to rolling brownouts. So there are brownout predictors that can identify not so much from catastrophic failures in the grid, but from high energy use days. So a high air conditioning day, for example, where we could use Facebook or other social applications to notify people selectively and let them know, hey, it's really important you do something about this today, and use that as a feedback mechanism. And this gets also to this idea of social reinforcement. Back to Tom's work, Tom wanted to develop a model that could be plugged into our existing grid models to look at what actually influences energy consumption and energy conservation behavior. Unfortunately, this is a pretty tough thing to model when you've got to validate it. It's easy to put together a BaseNet type of model like I've done with the EPA work, but when you've actually got to validate this down to a high degree of precision, it's not as useful a technique. So what he did instead was take a look at a correlative model built on the Residential Energy Consumption Survey. As it says here, there have been 12 surveys since '78. Unfortunately, the most recent is still 5 years ago. And the REX behavioral variables were looked at as a model for data collection and smart grid demonstrations, basically looking at what are the kinds of data we might want to collect in a smart grid pilot to better be able to understand how people respond to different smart grid signals. In the interest of time, I'm just going to put that slide up there. You can take a look at it real quick, but we'll go to another eye test chart in just a second that looks at the result. Of course, we have to go in with a basic model for how you think the world behaves, and Tom's was that electricity demand was a function of a number of variables, including energy price, location, all these external variables, dwelling and age types, but also that there were individual determinants, attitudes, beliefs, and behavior patterns. Household characteristics, including income, household size, age of the household members, and consumer choices. So what we did was ingest the entire REX 2005 data set. We removed missing values, did some recoding geographically to allow us to look at reconciling some differences between the way REX aggregates people geographically, and the way the power grid does that, and the way that climate zones do that. Selected a set of single-family homes and did a principal component analysis over that data. What you see here, again, is an I-test chart, but it basically says that out of this principal component analysis, starting out with approximately 30 variables, you can reduce this to a set of reasonably well-correlated factors that are aggregates of each of these variables. So for any one of these, the boxes that are in the green are simply the variables that were co-correlated together and seem to relate to a factor that made some intuitive sense. So, for example, for our affluence factor, we've got household income, total square feet, all correlating at around the 0.7 to 0.6 range. From physical sciences perspective, man, that doesn't look like a very high correlation factor to me, but my social science friends seem to be more happy to accept them. And because I know people have to get going, we'll kind of rush through some of this. What we find out is that almost all the variance was due to just 4 factors. One is the appliance use factor, which got to how many appliances you have in the household, and the patterns of uses, how many homes or how many rooms within the household they were found in. So how many televisions do you own? Are the televisions in bedrooms, or are they in the main living rooms? Things like that. The affluence factor, which gets to not only and the appliance use factor was also heavily dominated by laundry issues, believe it or not, which makes a certain amount of sense when you think about household energy use. Washing and drying clothes are actually one of the major consumers of electricity within the household in electrically heated houses. The affluence factor got into the number of appliances. Electricity price was simply taken as a separate variable, and then the climate factor got into the number of degree heating days and degree cooling days, which also got into behavioral issues. What you saw, though, was there's very little variance accounted for by things like insulation, which is non-intuitive. You would have expected that to be a bigger issue. The age of the house, the age of the household members. But when you look at this, take a second look back, what you find out is that aside from the price, each of those top 4 factors has a pretty strong behavior and lifestyle component to it. So the appliance use factor is dominated by laundry habits. Affluence factor dominated by the proliferation of appliances and gadgets. How many chargers do I have running in my house at one time? You know, what's my phantom load in that household? And the climate factor dominated by people's tolerance for heating and cooling. What's their comfort zone? Can they operate within a broad zone of temperature and humidity parameters, or do they want it at 70 degrees plus or minus 1 degree year in and year out, season in and season out? And also things like meal scheduling. There's all sorts of evidence to show that scheduling meals for later in the evening in certain climates can make a big impact on the amount of heating or cooling needed in the house. So this was simply used to identify where utility companies might collect more data from smart grid projects, and was built into our grid models to look at how we might create new incentives, new outreach and education programs that better target where the energy is actually used and how energy is actually used within the context of smart grid projects. Finally, I'm going to take a real quick look at climate change and food availability. This work, I should mention, is done by Liz Malone. Liz is one of our researchers back at JGRI, which is the Joint Global Change Research Institute. It's a joint institute we operate with the University of Maryland at College Park, and is where most of our climate change economists work. This is motivated not only by sustainability concerns, but by national security concerns. This is an area of significant interest to a lot of our intelligence community clients, who you can see some quotes up here that look at sort of the position of that community of people. I'll focus. Yeah, This one, we judge global climate change will have wide-ranging implications for U.S. national security interests over the next 20 years, and that the most significant impacts will be indirect and result from climate-driven effects on other countries and their potential to affect U.S. interests. A very good example is the one we're just going to look at in a moment here, which is the whole region of Pakistan, Bangladesh, and India, and the sensitivity of that region to climate change scenarios. In particular, as I mentioned before, it's been projected that under the mid and high level cases of sea level rise, that Bangladesh could lose habitable the worst case projections or even the mid case projections for sea level rise are actually realized. So that's a pretty significant number of people being displaced. It's a significant amount of agricultural land being taken out of production. And it's a significant impact socially on the stability of that whole region, because the countries in that region that I've listed all interact with one another based on a variety of issues. Not all of them are related to resource use, but ultimately resource use drives a lot of attention. So Liz set out to look at basically the issues related to the impact of climate change on agricultural production and water resources in the Indian subcontinent. The approach was to integrate information from models in different domains. I mentioned before that, lost my mic? Okay. So I mentioned earlier that the objective for this effort was to integrate models at the social and technical level. And in this case, they integrated models for energy and economic modeling with our EPIC model, which is agricultural model, which looks at agricultural production capacity at, I believe it's like 1 kilometer grid size around the world. And then a model that was developed specifically for this effort, which looked at stressors on political stability of countries and the sustainability metrics from things like the World Resources Institute Sustainability Metrics Project. And whether or not the changes that occurred in agricultural production would have impacts on the stability of the governments in each of these countries. And I'm not going to address the knowledge encapsulation framework. Here we use Stella, which is a systems dynamic model. I can't even read this one. But essentially what we did was we divided the model up into a simplified version of land and crop production, looking at the response of crop production to a number of different inputs, including climate change scenario, sea level rise, and average temperature and rainfall. Looked at policies related to food and biofuel production. This was essentially looking at where was the emphasis placed from a policy standpoint relative to growing food crops versus growing energy crops. And then looking at how that affected nutrition and the availability of food. What was interesting about this project is that we actually took this model and plugged it into a video game that was then given to analysts who worked for CIA and a couple of other agencies. And they were using that essentially to game out different scenarios. Not with the and one of the things that's important, and I think this is useful to note because I don't always admit this publicly, but the use of the social models in this case is more useful for the process of thinking and diving into the problem than it is for the actual results they produce. Using the models and pushing the analysts through the process of testing, critiquing, and creating the models forces them to think more critically, and critically in a different way, about how these systems interact with one another than if you were simply to sit down and try to extract their knowledge by some other means. We've often found that the models themselves are pretty disposable, but that the process of leading people through the creation of the models is where the value gained. Okay, let's see. So that's an admittedly very brief discussion of Liz's work, and I apologize. Her project ended about 2 years ago, and I wasn't able to get a hold of Liz to get her last set of publications, which include a little bit more on the results side. But it gives you a general idea of how we've used social modeling, in this case, the use of a very broad brush model for governability and sustainability of a society or an entire region of the world, based on inputs from the technical sphere, from agricultural production, from climate, and from energy resource use. And also limits to some degree, or put some bounds, I think, around where we think the utility of that model is, which is not in making concrete or precise predictions about where the world is going to be in 50 years, but rather looking at the trends and patterns and the interplay between variables, which I think was a useful outcome of the project. So in terms of future direction, I've mentioned a couple of the things we're looking at right now already, the role of social media, especially on the smart grid. How do we use social media to get word out, to engage people where they're often more tuned in? What's the average? I think the average for the number of times that a US Facebook user hits the refresh button is something like 12 times per day. And I know certain friends, and maybe counted amongst those myself, that's more like 12 times per hour on a slow hour in the evening. So how do we take advantage of that to deliver the positive reinforcement, this normative calibration to how other people are using energy? And ironically, we want to do that through a device that consumes energy, but, you know, interesting paradox, but probably not significant in the long run. How do we provide meaningful feedback to people, not only through the social media, but through interface design? We have a large group that works on human-computer interactions, and we're currently spending a lot of time looking at how information analysts respond to and use information, but we've also been taking a look at how do we use that for instrumentation at the household level, trying to take some of the things we've learned from work with the Nuclear Regulatory Commission to make instrumentation at nuclear plants more useful and more effective, and translate that to the household level of how do you get people to pay more attention to a smart thermostat that actually talks back to them. Because technologically, we have the ability to do that. How do we predict things like group behavior? So how do we predict the behavior of people in large groups in terms of their response to the social media message we talked about, to changes in technology, to changes in power availability, and in changes to price? Economists have focused on the response to price for a long time, but people aren't driven solely by price on their use of energy. And so how do we look at the other factors that play into that? I mentioned that my own area of interest largely dwells in the area of life cycle analysis, and particularly consequential life cycle analysis. As a national laboratory, we're primarily a group of technology providers, and so we're almost always working on what are typically dubbed by DOE transformative technologies, so solid oxide fuel cells, other kinds of fuel cell technologies, advanced materials, nanotechnology, and biofuels are just a couple of examples. How do we look at unintended consequences that might be down the road for those technologies once they go out of the laboratory and actually go into widespread production? How do we anticipate the kinds of stumbling blocks that nano is encountering, for example, in some parts of the world in response to the precautionary principle? How do we anticipate the kind of response that genetically modified organisms are encountering? Because some of these technologies have enormous potential to save a large amount of energy or to reduce a large amount of waste or operate more resource efficiently, but only if the technologies actually get deployed, and only if we anticipate correctly the downstream unintended consequences. And then, of course, in the near term and for right now, I'm working very directly on this issue of understanding technical assistance effectiveness, and particularly trying to model in a causal way, or at least a semi-causal way, how technical assistance changes behavior downstream, when we all know that a company doesn't make a change in response only to the technical assistance I've provided, but hopefully the program has some impact on the technologies they adopt and how they behave. How do I decide what portion of that the behavior change actually comes from what I've done as a technical assistance provider, and how do I use the insights that I gain from modeling that to improve the delivery of technical assistance and make good predictions about how that assistance is going to pay off in out years, because currently there's not a big investment being made in this area, even though there's a huge opportunity. So that's it. Yep, that's the last slide. I appreciate your patience. I'm sorry for running so late, but I'm happy to stick around and answer any questions or just bounce ideas back and forth for anyone who wants to do that.
First, we'll give Scott a round of applause. And if anyone has questions or if you need to leave, questions from anyone?
Yes, sir.
What about anything done with cap and trade?
With cap and trade?
Yeah, with the impact, what...
So the question is whether we've been doing anything with cap and trade, and
any equations, or...
There's been a fair amount of modeling in that area back at JGRI, our Joint Global Change group. Jay Edmonds and the rest of the gang back there have been involved with looking at the different scenarios under cap and trade, different policy options for some time, but I'm not very familiar with any of it, so I really can't speak to it, but I can certainly point you at the people who are...
I can talk to you.
Okay. Other questions? None? I'm sorry, I exhausted you guys. Or okay, there's one. Yeah.
How much of an impact does popular media like movies and whatnot have on getting people to change their technology, like movies like Terminator or Assassin's
I heard the first part. So the basic question, if I understand, is how much of an impact does popular media have on getting people to change their behavior? And I didn't hear the examples.
Oh, well, like Terminator with Skynet, like make people look for the electronics.
Oh, okay.
Or like, there's all sorts of like things about biological hazards that we engineer.
You know, that's a great question, and actually would be a fun set of research projects to do, I think. Clearly, from a stance of sort of setting social norms or establishing what's normative behavior, there's good evidence to support that has a big impact on how people use energy. But beyond that, in terms of setting attitudes about technologies, I mean, clearly there's an impact there. How much of it is causative, I don't know. I mean, a good example would be China Syndrome, the movie China Syndrome, and every other movie about nuclear disasters feeds into what's already known in the research literature about how people interpret different kinds of risks. And people are disproportionately afraid. If you look at from a risk science standpoint, if you sit down and actually calculate out the statistics, and you can question the statistics, but they're orders of magnitudes worth of differences. Look at the statistics of the risks posed by a nuclear power plant and a coal power plant in my backyard. You know, you'd vastly prefer to live next to the nuclear power plant. And yet that's not how people perceive them. It's not how people are perceiving the situation in Japan right now. I mean, face it, 10,000, 15,000 people died over the last 2 or 3 weeks in Japan as a result of things totally unrelated to the nuclear power plant accident. And yet our fears and our concerns are dominated almost exclusively by what's going on at Fukushima, which will have almost no impact on anyone outside of about a 20-mile radius. Or at least we hope not. I don't know. Every time I say that, I'm not necessarily a big advocate for nuclear power, but I live around it and have worked around it, so I'm less afraid of it. But every time I think that that we've reached the worst-case scenario at Fukushima, it just seems like it gets worse and worse. And I actually think that will be one of the largest downwind or down the road impacts, I guess. Downwind might not be the best choice of words. is that it will make us all, I think, any rational person, rethink our idea of worst case. And I think that will have a bigger impact than the actual physical impacts of the plant, because it's going to have a huge impact, I think, on the U.S. nuclear industry and the European nuclear industry, at a time when even Greenpeace was starting to begrudgingly admit that nuclear might need to be part of a climate change solution that was viable. So back to your question, I guess. How did I get there? Oh, I got there because clearly popular media has some connection to the way we perceive those kinds of risks.
I know a lot of people who are like, oh yeah, you know stuff about DNA, but I saw it on CSI and you're wrong.
That's right.
Yeah.
That's right.
It takes 2 minutes.
And we do live in a society that's borders on technically illiterate, scientifically illiterate. I wouldn't say borders on it. It is. Yeah, you're right. But how much it can actually be turned around, and we've had this discussion in a couple of P2 meetings, pollution prevention meetings I've been to. What would it take to create sort of a new literature, a new set of movie icons or movie archetypes that would change that whole? Oh, absolutely. Well, actually, it would have to involve asteroids or volcanoes, I think, on Sci-Fi Channel. I think.
Oh, they do a whole slew of things.
Okay.
My husband's a big fan.
Oh, my wife is too, and I don't watch the movies very closely, but it seems like everything has to revolve around some sort of natural disaster.
I don't know, there's a lot with like the mutant gators. They
Okay.
have
Oh, I forgot about the gator movies.
exposed
That's
to
right.
some type of biological contaminant that we can grow 20 times larger.
Okay, so we tie those to persistent organic pollutants, and we've got it solved. Okay.
But you're right, this weekend was Meteor Weekend.
Yes.
It's all about meteors.
I'm sorry. Any other questions? This could get.
Do you think that the actual number feedback plays on the science theory? The theory is that in denial, like in climate change denial or anti-smoking denial, that a lot of it's based on saying that the science is opinion-based and not fact-based. Do you think that the numbers versus the recommendations of behavior attack that idea that it becomes a fact rather than an opinion that is happening?
There's a part. Okay, so the question is, will, and I'm only repeating the questions to make sure. Well, partly to make sure I understood it, but also so that we capture it for the audio there. So the question basically gets to if we have better data, can we somehow put to rest scientific or supposed scientific debates over the reality of things such as global climate change? And at one time I believed that, yeah, we could, that we just needed better data. I guess intuitively and just from watching the news, from watching political discussion boards, I don't believe that it's likely to change that. We have petabytes worth of data to back up the notion of global warming, and yet there's still a large number of skeptics out there who will deny that, although one fewer than there were last week. And for those of you who didn't hear about that, one of the leading climate skeptics just announced during his testimony to Congress last week that he had reviewed a large body of data and actually found that his analysis was consistent with the analyses that have already been published showing global climate change trends were in fact happening, and that his analysis didn't come up with anything that was significantly different from those data, despite the fact that he'd spent years trying to discredit it. So one fewer skeptic as of a week ago. But I think there's a great deal of interesting psychological research, and I would guess that our colleagues in marketing and especially in political marketing probably are years ahead of us in terms of understanding how belief versus fact influence behavior. It's not an area where I've spent a lot of time. Our social modeling work has tended to look at group behavior and things like group identity theory. How do people choose which groups they affiliate with? a lot of it actually in applications outside outside of environmental issues is looking at things like how do groups become radicalized politically, and not so much at individual belief and behavior, which I think is more in the realm of psychology. That being said, I think we're understanding that better and better all the time. And brain science is making huge leaps and bounds, but whether or not that changes human nature, I don't know. I don't think so.